All right.
So Justin, take it away.
Thanks, Frank. All right. So as Frank said, I'm going to be talking to you about how solar EUV affects Mars. So I don't have any solar spectra in this talk. What I'll be doing is telling you about some of the observations we've made at Mars with the Maven mission over the past 6 years or so, and talking about how we've seen the influence of the sun at solar EUV wavelengths in the upper atmosphere of Mars. So I think a lot of people here may not be familiar with the vital statistics on Mars. I don't really expect anyone to read through this slide, but this is just sort of the standard comparison, the planetary comparison that you see at the start of a lot of Mars talks. And, you know, in some ways, Mars is kind of similar to Earth. In a lot of ways, it's very different. And so I'll be going through some of those differences in this talk, especially how they influence the way that the solar UV that is absorbed in the upper atmosphere is processed, re-emitted, what photochemistry it participates in, and things like that. And so maybe a couple of things that are worth pointing out on this slide is that Mars does have a similar day, a diurnal rotation period to the Earth. So, you know, in terms of diurnal dynamics with the thermosphere, you'll see some similarities in response. But also note that it is much smaller and it is much colder at Mars. And the atmosphere has a very different composition, dominated by a CO2 atmosphere. And that's going to be very important in the way that the solar UV energy is processed. So why do Martians care about solar EUV? So I'm coming at this from the point of view as a Mars scientist. And so, you know, a lot of the Mars community is obsessed with geology, surface processes, but they actually do care about solar EUV as well. And the reason is that we have this abundant evidence from multiple lines of inquiry that at Mars, there was at some point in the past, liquid water on the surface and most likely a substantially thicker atmosphere than there is at the present day. And so just two snapshots to illustrate this from recent missions. On the left is a picture of what we call mud rock, or it's a kind of sedimentary rock that you typically find at the bottom of a lake where there's been standing water over a long period of time. And this is something that, that you can find on the Earth. And the Curiosity rover at Mars has found this in Gale Crater. On the right, we have a different fluvial feature here where we've got a delta. There's a river channel, a dry river channel coming in here, and then a beautiful little delta. It's actually not that little. This is in Jezero Crater, and this is where the new Perseverance rover has landed. And this is another geologic feature that tells us there was long-term liquid water on Mars at some time in the past. And so there's an open question as to what changed. How did Mars wind up as a dry, cold desert now if this was different in the past? And so atmospheric escape is a big part of answering that question. And that goes directly into why we care about the solar EUV, because if you're going to remove atmosphere from a planet, it's either got to go down into the surface, and that certainly happens at Mars and other planets, but it can also go out into space. And if it's going to go out into space, there's some criteria that have to be met. One is that the escape has to occur in a region of atmosphere where there aren't a lot of collisions. So this is what we call the exosphere, right? And then the atoms or molecules have to have enough energy to leave the planet. And for Mars, this is an escape velocity of 5 kilometers per second. And since solar UV radiation is the primary energy source in this region of the upper atmosphere and a critical driver of the vertical structure there, it means that we have to understand how the solar UV radiation is absorbed and that energy is partitioned in the upper atmosphere if we're going to understand how Mars has evolved over the history of the solar system. All right, so the data I'll show you today was collected by the Mars Volatile and Evolution Mission, or Maven. There's a whole suite of instruments for both looking at the sun and looking at charged and neutral particles in the upper atmosphere. The only instrument that directly observes the solar EUV is the appropriately named EUV, or actually I think we call it EUVM now. And then I'll be showing some results from all these other instruments and how they correlate with events seen by EUVM. So I've broken out 4 processes to talk about for Mars specifically. And so we'll just go through these one by one. I'll have an example of how things work at Mars, then an example of how variability in the sun drives changes. So first up, excitation. So roughly 1/5 of the solar EUV absorbed in the upper atmosphere of Mars is just pretty quickly re-emitted at longer UV wavelengths. So in the far ultraviolet and the mid ultraviolet. This is a spectrum, a set of spectra from the 2 channels of the IUVS instrument. I'm a team member on that instrument on Maven. This is an ultraviolet spectrometer. And this is what we call the air glow layer. And it's primarily powered by the solar EUV. So this is most of the spectral features that you see here are products of CO2 dissociation. There's some nitrogen features. There's some ion features, and this is one way that the energy deposited in the upper atmosphere gets re-emitted. Just a quick plug, this is the only non-Maven data in this talk. This is some recent images from the Emirates Mars mission, which has its own ultraviolet spectrometer. I'm also associated with that instrument team. And this just gives a nice pretty picture of some of the different wavelengths that we see ultraviolet emission at Mars driven by the solar EUV. And so these are very useful in probing the composition, the structure, and the photochemistry of the Martian upper atmosphere. So that's all I'm going to say about excitation. One of the other major ways that absorbs solar EUV is deposited is through dissociation. And so since CO2 is the dominant species in the Martian atmosphere, most of the solar EUV is absorbed by CO2, and it breaks it apart into a CO and an O CO molecule and an O atom. These do not immediately recombine. They have to work their way down into the lower atmosphere where it's collisional. And so what happens is that O and CO accumulate in the upper atmosphere. You can see this in data from our NGIMS instrument on Maven, the neutral gas and ion mass spectrometer. And you can see here that oxygen kind of takes over at higher altitudes. This is in red, whereas CO2 is more abundant lower down. And you've also got nitrogen and carbon monoxide and a few other photochemically inert species. And so Maven's getting lots of good data, monitoring the profiles of these species. And one of the most interesting recent publications on this, so just last year, there was a flare, an X-class flare, X8.2, I believe it was, that impacted Mars back in September of 2017. And this has been a really fruitful event for publications and understanding Mars. This particular one is one of the most recent analyses, and it shows how the composition changed as measured by NGIMS before and during the flare event. And you can see that we have on the left the profiles themselves, sort of typical profiles, and then the flare orbit in dashed curves. This is for a vertical axis, we have the total number density here instead of altitude or pressure or something like that. And so maybe more obvious is this relative change where you can see that the abundance of atomic oxygen went up pretty dramatically while the heavier species were depressed during the flare event. And so some of this may be photochemical. Some of it may also be due to structural changes due to heating caused by the flare. And we'll talk about that a little bit more later. But this is one of the neat new results that Maven has produced recently. Oh, one other thing on dissociation. So at Mars, CO2 is not the only molecule in town. There's also nitrogen. And so what can happen is when those oxygen atoms come off of the CO2 and N atoms come off the N2, they can be transported around to the night side of the planet. And when they are, they can recombine and form a new molecule, nitric oxide, which is in an excited state initially. And so it emits an ultraviolet photon. We call this night glow. And the IUVS instrument has been able to map this out. I'm just going to run this video here. This is a false color, obviously. The photons aren't green. They're actually at around 200 nanometers wavelength. But this is showing variations in the nitric oxide night glow. This is primarily due to circulation patterns in the upper atmosphere because these two atoms, the N and O, need a third body to collide with to recombine to conserve angular momentum. And so this is primarily showing us circulation patterns in the middle atmosphere of Mars, but it's all driven, it's all powered by the solar EUV on the day side. Okay, next up we have ionization. And so, you know, any planet with an atmosphere, it's going to have an upper region where the solar EUV is ionizing the neutrals. And so Mars is no different. So it has an ionosphere. One of the things is that the ionosphere has its own peculiarity. And so we have a pop quiz here. What is the dominant ion in the Martian ionosphere? I'm not sure I can look at the chat at the same time. If anyone wants to take a guess, A, B, or C, or maybe just think about it for a second. You might think CO2 plus. CO2 is the most abundant neutral. Most of the ions produced should be CO2 plus, right? Or maybe it's O plus. Maybe it's like Earth's ionosphere. You know, it's a terrestrial planet. Why not? Or O2 plus. I don't know why it'd be O2 plus, but it is O2 plus. Okay, so why is it O2 plus? So we can see this. This has actually been known since Viking, but it's borne out in the Maven observations of the ion species. And the reason is pretty well understood too. It's charge exchange reactions. So it is true that most of the initial ions produced by absorption of solar EUV are CO2 plus. There's some O2 plus, there's some O plus as well, but those ions undergo charge exchange reactions pretty efficiently and wind up as O2 plus. And O2 plus becomes what we call the terminal ion because there are very few species in the Martian upper atmosphere that have a lower ionization energy. So ions that can charge exchange to produce O2 plus do so, and then it just sits there as an O2 plus ion. And you can see that it's a pretty dramatic, pretty efficient process. It's well over an order of magnitude here, more abundant than most other species. So that is interesting because O2 plus is a molecular ion, and so it can undergo dissociative recombination, where when it recombines with an electron to neutralize, the diatomic molecule actually dissociates. It breaks the bond between the two O atoms. And they can have sufficient energy to escape from the planet, depending on the partitioning of that energy into electronic states. And so this oxygen forms what we call a corona. This is a planetary corona, right? It doesn't have anything to do with the solar corona around Mars. And we've seen this in multiple data sets. On the left, I have a paper I published several years ago showing the oxygen seen by the IUVS instrument. Low down, we see the thermal oxygen. So this is like 200, 300 Kelvin. But then there's this slope change in the vertical profile and sort of an effective temperature of like 6,000 to 8,000 Kelvin. And this is produced by these photochemical reactions. We also see this in pickup ions in the particle instruments. This requires a lot of averaging. Actually, both methods to get the most out of them require a lot of averaging. But the pickup ions can track oxygen at even higher altitudes. And this is just to show you, I think I'm running out of time here, but this is just to show you that we can track this across the Maven mission to date. We have in light blue here and in the lavender, 2 of the channels on the EUVM instrument, which monitors the solar flux at Mars. And then a timeline in gray, we have one of those ion airglow features in the IUVS data. And then in the sort of tomato in the red is a way of tracking that hot oxygen corona. And the black is a model to kind of pick out variations in sampling due to the precession of the Maven orbit. But if you just look at the red points, which are near the subsolar point, and the gray points, and compare them to these EUVM measurements, you can see that the airglow and the density of the hot oxygen corona are tracking with the solar activity. There's a few things going on here. The general over decline is due to the end of the declining phase of the solar cycle. This modulation here is due to the Mars-Sun distance. Mars has a fairly elliptical orbit around the sun. And then you can also see some 27-day rotation features in here as well. So that's all good stuff. All right, I'll quickly say something about heating, which is that about 30% of the absorbed solar UV is deposited as heat in the thermosphere. It's often a cascade process from these other processes. We see variations depending on how close you are to the subsolar point. This is shown here in these density profiles from NGIMS data done by Shane Stone. And most of the energy in the upper atmosphere, this is a model on the right here. You can see most of the energy here on the day side. This is UV, solar UV heating, and it's balanced partly by thermal conduction, but also by CO2 radiative cooling. CO2 is a very good emitter of radiation, and so it actively cools the upper atmosphere. And that's why these temperatures are so much lower than at Earth, right? At Earth, we'd be looking at 500, 1000 K, maybe higher. These are much cooler because the CO2 emits the energy efficiently. Just a quick word that the heating of the upper atmosphere can drive escape directly, especially for lighter species like hydrogen. And it's just because the Maxwell-Boltzmann distribution has a tail. And this is this hydrogen corona that IUVS has been able to image. This is work by Mike Chaffin, also at LASP, on the IUVS team. And so that's another important way that solar EUV drives escape from Mars. And again, like with the ionization, we can track this across the mission. And so this is a very similar picture to the one for the ionization. I'm not going to go into any detail. This is by Sonal Jain. It's in preparation for submission in the next few days. And then one previously published result specific to impulsive events, that flare I mentioned earlier, the 2017 flare, X-class flare, we did see a dramatic increase in thermospheric temperature. So this is the sort of the baseline here. Here's the orbit closest to when the flare occurred. And here's a little inset with a contextual reference of what the EUVM X-ray channel saw compared to the temperature trend. So in summary, the absorption of solar UV radiation in the upper atmosphere of Mars is important for understanding the impact of atmospheric loss on the planet's evolution. And that solar UV radiation drives a rich variety of processes. And we walked through those. And the Maven mission has and continues to greatly deepen our understanding of the Martian upper atmosphere and the role of solar inputs, including and especially solar UV radiation. So that's all I've got. I'll take questions.
Thanks, Justin. I'm looking through the chat to see if anybody asked a question other than me. So I asked the question or made the statement that Stan Solomon often says that if he knows helium-2 304, he can know most of the variability of the Earth's upper atmosphere. Is that true for Mars and its different composition atmosphere? And if not, is there another wavelength that matters more?
No, I think that's probably true for Mars as well. The the ionization potential for the CO2 and the O aren't super duper different from the O2 and the N2. And so all the photoelectron stuff, there's some nuances there. But I think it's a true statement that this would work at Mars. If you take into account all the differences, it's still true.
Okay, and another question that I posted for all the speakers actually to think about is, at least for your science, what is the ideal thing to measure? What would you like to know from the sun for the input to the Mars atmosphere that you don't know right now?
That's a good question. Do you want me to answer it right now or save it for later?
You could think about it and talk about it during the
Yeah,
break.
that sounds good. Give it some thought.
I see one question from Liang. Says, is there infrared cooling in the Mars upper atmosphere to balance the solar EUV heating?
Yes, there is that. Oh no, it's not going to let me go back. That was this slide here. This purple line here is a CO2 radiative cooling in the infrared. So this is a 15 micron line doing the cooling. So it's different from Earth. The oxygen 63 micron line is there, I guess technically, but the CO2 15 micron does the heavy lifting at Mars.
Does NO play a role on Mars in cooling?
In cooling, I haven't seen evidence that it's very important. The NO tends to pick up as you go lower down, but at that point, the radiative cooling, you start picking up infrared heating, near infrared heating. And there's just so much more CO2 and it's so good at transferring heat. Like this just kind of explodes. This purple curve here would just explode to huge values for cooling as you go down.
Okay, let's move on. Thank you, Justin, very much.
You're welcome.